All right, I'm going to go ahead and start just with some definitions here. Extreme value theorem. The purpose of it is to find the max and mins, the highest and lowest y values on the closed interval. So a function is continuous. That's the only condition for EVT. There's no differentiable for EVT because it doesn't require slope to find as long as the graph is connected. It's good. All that matters. Interval is bracket. Okay, mean value theorem. And Rolle's theorem. Mean value theorem, you're trying to guarantee a slope on the graph. Rolle's theorem, you're also guaranteeing a slope on the graph, but the slope has to be 0 that you're looking for. Okay. So we always find the slope between the endpoints. So, and once we find the slope between the endpoints, then the slope could be 2, it could be 1/2, it could be 3. But whatever slope you find here, you're going to look for it somewhere along the curve by setting it equal to the derivative. So once you do that, then you can find that slope that you drew between the two endpoints. Okay, Rolle's theorem. Almost identical to mean value theorem, but instead of a slope that could be 3 or 2 or 1/2 or -5, the slope has to be 0. So in order for us to draw a slope 0 between the endpoints have to have the same y value. But the conditions initially are the same. Okay, so we still find the endpoints. We technically could do f of b minus f of a over b minus a, but if the endpoints are the same, then we know this value is always going to end up being 0. So it's a f prime equal to 0 because this piece will always land be 0 if my numerator is always the same y value. Solve for C. Okay, number 1, if the function 2x over x squared plus 1 is on the closed interval from -2 to 2, determine the max and min values on the graph. This is a extreme value theorem. We have the function on the closed interval. Okay, so the one condition that EVT has is that the our graph has to be continuous on the closed interval, and we see that there is a denominator which could be an issue. So we always want to potentially look for some vertical asymptotes, but if I try to do that, let us see something that doesn't quite work, right? I can't take the square root of a negative number. There is nothing that's going to cause this denominator to be 0. There's no vertical asymptote. We're safe. The one condition that we have, we're going to be able to make it pass. So with EBT, we have to consider the endpoints and the critical points. We can save the endpoints for later. We already know what they are. We have to look for the critical points, though. So critical points comes from the derivative. From the derivative, this is going to have to be quotient rule here. F prime g minus f g prime all over g squared. Okay, expand this out. All right, so once we have our derivative, we know we're looking for critical points from the numerator and the denominator. If we set the denominator equal to 0, nothing will come of it because we experienced that when we tried to look for something in the denominator. But really, the numerator is going to be the one in this case that's going to produce some critical points for us. So x equals 1 and -1. Right, we have 2 critical points, but we have to always make sure that the critical points that we find are valid. Right, anything that's outside the interval, we don't care. That's not part of our problem. But both 1 and -1 are inside the interval from -2 to 2. So we're going to test these 2 critical points and the 2 endpoints to see which point has the highest y value or lowest y value. So we have to take these values, insert back into the original function. Okay, so everything just goes back into the original function here. Use your calculator. Okay, so between these values here, we're looking for the highest and lowest y value. Highest y value is 1. Lowest y value is -1. Just the y values. Okay, Rolle's theorem. Okay, we got a polynomial here. We know our function is good. no issues with our conditions, except we got to consider the endpoints, see if they are producing the same y values. We'll do that soon. They both give me y values there. We know the slope is 0. Okay, so now going on to the derivative, I went through product rule, but you could just easily FOIL all this out. But if you want to FOIL it out, make sure you do 2 at a time. So let's do the x plus 2 times x plus 2, FOIL that out, and then distribute the x minus 3 through. You'll get the same result as going through product rule. Okay, if I FOIL all this out here, x plus 2 times x plus 2. Factor, both by to be negative 24. That's it to be 2. Six and 4, reduce the parts that you can. Okay, so once we look at our potential C values, we only want to keep the location that's actually living between the endpoints. -2 is close, but it's not good enough. An endpoint is not, our C value has to be on the open interval. So -2 is almost there, but not quite. C is 4/3.
Would you like able to be both as like 2?
If it was like -1.9, it would be good
Oh,
enough.
okay.
Right. Yeah, but as long as it's inside that endpoint, we're okay. If it's right at the endpoint or outside of it, we have to remove it. Number 3. Number 3 is mean value theorem, almost identical to Rolle's theorem. It's just that we're still going to find the endpoints, but the endpoints don't have to give us the same y value, which means that our slope is going to be different, potentially, most likely, than just 0. But we still set f prime equal to whatever slope that we find. Just that with Rolle's, it has to be f prime equal to 0. With mean value theorem, it's f prime equal to whatever you gathered slope. Okay, conditions look good. Okay, spend the time to find the endpoints. Okay, so the slope between the endpoints is change in y over change in x. Okay, we will come back to this. We're going to need that value later. Let's find f prime. So we're setting f prime equal to the slope. Make sure that you insert the slope into the f prime slot and not into the x, right? So this -1 is going to go here. Okay, I see some people do this where they try to factor this side and set equal to -1. What's the issue here?
Gotta add -1.
Right. If we want to do any factoring, we can't do it unless this is showing a what? 0, right? So we gotta, if we see something that's out of place, we gotta go ahead and move it. Times c is -1, b is -2, multiplies to be -3, adds to be -2. Sorry, 1, not 0. All right, so again, we run into the issue as the previous problem is that 1 is a little bit outside the interval. So we're only going to keep this -1/3. Okay, number 4. Okay, we got a derivative graph here, so if we're looking at the derivative graph, we're going to create solid lines for f prime and f double prime. Make sure we remember what we're dealing with here: above the x-axis, below the x-axis. Okay, so we're looking for slope 0 first. So we just have to make our best estimation here. But on the test, it'll be clear. So here, that's 1. I'll call this close to 3, like 2.8. And this is, I'll call it 5.7. But okay, don't look at the movement of the graph. Look at the location of the graph. Is the graph above or below the x-axis? We see that it starts off below the x-axis, so we know that's going to correspond with that that arrow moving down, negative slope. Between 1 and 2.8, the graph is clearly above the x-axis, positive slope. Between 2.8 and 5.7, below the x-axis, negative slope. And to the right of 5.7, above the x-axis, positive slope. Okay, second derivative sine line. If I want to find concavity off of my derivative graph, the way we start is we look for the peaks and valleys. Don't look at the curvature. You're looking at the peaks and valleys. That will tell you where your points of inflections are. Two and 4. To the left of my peak, I want to look at the slope. So the slope of my derivative graph is going to translate to the concavity. So here, this is a positive slope. Positive slope means concave up. Negative slope, this is what a lot of students want to do though. They want to look at this and say, well, this looks like concave up, so I'm going to say concave up. Okay, don't look at the shape of the graph because this is not the original function. Okay, look at the slope. This is a negative slope. Means concave down. Positive slope is concave up. Now there's something strange here. This is a horizontal line. I'm not going to quite get this to you on the test, but I just want to kind of show you here. What is this? This is not a slope.
Constant slope.
Yeah, you see that this is, remember the y-axis represents slope. So basically the graph is going to just kind of flatten out and just have a slope of 1. So it's just going to all of a sudden from a curve turns into a slanted line because that graph is going to hold a slope of 0 for this on the graph. And slope of 1 is going to look like a slanted graph, right? Like 45-degree angle. So let's sketch our graph here. We don't know the y values, but we can figure out the shape of the graph. Right now, we're going to create something that matches what we expect from the shape. Okay, so we know we want a relative minimum at 1. So I'm just going to create a low point for me to target. At 2.8, I'm going to be expecting a relative max. So 2.8, I will exaggerate it with a high y value. 5.7, I'm going to make this a lower y value here. Okay, so I'm going to do 2 versions of the graph. I just want to do a dotted line just to kind of get my graph going here. I know it's not my final draft, but it will kind of give me something to work off of. Okay, so now we can sketch our graph. Well, let's target some points for us to go after here. 2, wherever the graph lands at 2. So at 2, the graph looks like, for me, it's somewhere up here. 4 is somewhere over here. So that kind of gives me some target points because I know that across this graph, my graph is going to change its curvature as it hit those points. So first, it's going to start off as concave up. going to transfer over to, or transition over to concave down. And then from 4 on, it's going to be concave up. Right? But then for a slight moment there, the graph is going to just all of a sudden kind of turn into a slope 1. And slope 1 is just going to be a linear a line because of this. Say it again.
Why should put that point under negative?
Oh, let's see. Positive 1. Yeah, sorry about that. Positive 1. Graph's a little bit off. Okay, so my relative minimum should have been at 1, and then sketch my graph, concave up, concave down, concave up, and then slope 1. Okay, next page. Okay, so again, we have a derivative graph. Okay, we know that slope 0 is at A and B. Oh, sorry, my bad. Just A, right? Just A, because x-intercept is at A. So I'm going to create all these answer choices. Now, there's not going to be any multiple choice on the test, but I think it's good to just kind of practice through this problem here, because we still need to be able to gather information. So we know that at A, there's a slope 0 to the left. It's clearly below the x-axis. To the right is above the x-axis. So what do we expect? Expect what at A? Relative minimum, right? Because the graph is decreasing. I know it looks like it's rising, right? But this is not the original graph. So we have to make sure we interpret it correctly here. You know, there's a relative minimum at A. Second derivative sine line, we look at the peaks and valleys. There is no valley, there's only a peak. So we know that there is a POI here. And we look at the slope, right? Positive slope on the derivative graph means concave up on the original graph. Negative slope on the derivative graph means a negative concavity for second derivative. Okay, so relative minimum at A, a point of inflection at B. Okay, it's asking which of the following is not true. There's a relative minimum at x equals A, that's true. There's an absolute maximum at B. Well, we know that there is no absolute max, or there's not even you know, past B here, the graph is still increasing because the graph is still rising. So we know that there's no absolute max at B because the graph is continually rising past B. Right? It's going to keep going up. So there is it's false here. Okay, let's just go through the others to make sure here. Increasing from A to B, that's true. It's increasing any time to the right of A, because it's all above the x-axis. F double prime is positive from A to B. That's true, concave up. F double prime is equal to 0. So F double prime is equal to 0. That's a condition for point of inflection. And we know that the concavity is 0 because 0 slope, right? F double prime is equal to 0 at B, true. Okay, number 6, this is the original graph. So if this is the original graph, then everything that you see is what you expect, right? So relative max, relative min, relative max. Let's see our options here. F prime is greater than 0, so positive slope from D to F. That's true, right? This is the original graph, so everything that you see is straightforward. F double prime is equal to 0 at points B, D, and F. That's not true, right? F double prime equals 0 means point of inflection. These are not points of inflection. These are where slope is 0, not where F double prime is equal to 0. Okay, F double prime is greater than 0. Concave up from A to B. This doesn't look like concave up, right? It looks like concave down. Second derivative, concave up from D to F, from D to F. It is also false, right? We know that concavity is going to have to change. And by the time it hits F, it should be concave down, right? It's still not going to be concave up still. So this is still also false. Just one. Yeah. F double prime is greater than 0 on the interval from A to B. From A to B, now this is not the derivative graph. It is the original graph. So the original graph, this is obviously concave, part of a concave down graph, right? So it's not concave up, it's concave down. Find the relative extrema, or find the extrema. So relative extrema here. This is basically first derivative test, right? We can just have to set F prime equal to 0, create our slope sine lines, and then look to see which of these options we're dealing with. So F prime, go through power rule here, bring down the 3. Okay, go through your slope sine lines here. Test points. That's 0, 6, 8. Into the derivative function here. Negative times negative is positive. Plug 6 in, negative times positive is negative. Plug 8 in, positive and positive is positive. So based off the arrows, we can tell there must be a relative max at 5, a relative minimum at 7. There is no absolute max or absolute min because the graph is going to head to infinity in both directions, and we're not going to be able to pinpoint a specific real number here. So there's no absolute max, absolute min, relative max at 5, relative min at 7. Okay, number 8's pretty easy here. Find critical points. That just means you're just going to set f prime equal to 0 and just stop here. That's all that means, critical points. Yeah. Oh yeah, should have. You're right. I should have done that. This is not the right way to do it. Thanks. Okay, number 9 is messier than what I expect you to do on the test, but essentially, let's talk about the steps here. For number 9, to find the point of inflection, we have to first make our way down to the way. First and second derivative. Okay, so we find the first derivative, we find the second derivative. We set f double prime equal to 0. And then when we solve for x, let's say x gave me -4 and -2. Okay, so let's say x equals -4, -2. Can I just stop here and say, oh, these are for sure points of inflections? I still got to do what? Sign line. Okay. So you have to actually put those sign lines onto your second derivative number line here. And you also have to test and make sure that there's actually a change in signs. Okay. So you would plug in -5, -3, 0 into the second derivative function. See whether you get concave up or concave down. And if there is a change in sign here, there's got to be doesn't matter the order here, but as long as one side is different than the other side, then you know that's a point of inflection. Okay? But if the signs are the same on both sides, then it's going to have to be, we have to leave that alone. It's just going to be a critical point, but not a point of inflection. But here, point of inflection for both cases. Let me give you a different version of number 9 here. What if I gave this to you? Good. So if I'm looking at the second derivative graph, we can start off by understanding what we're working with here. Above the x-axis is concave up, below is concave down. Anything on the x-axis is potential point of inflection. But it's got to change signs, right? It's got to be able to flip to the other side. So if I try to create my sine line here, the left is above the x-axis, between A and B, still above the x-axis, to the right of B, below the x-axis. So A is a candidate, but it doesn't pass the test because it doesn't change signs on either side. Because left over prime changes signs. Okay, turn to page 26. This is the problem that you're going to have to be able to do on optimization. It will be a box problem finding minimum cost. Okay, construct a box whose base length is 3 times the base width. Okay, the material used to build the top and bottom cost $10 per square foot, and the material used to build the sides is $6 per square foot. If the box must have a volume of 50 cubic feet, determine the dimensions that will minimize the cost. We're trying to minimize cost, but again, we are the cost is coming from the material that is building the box and not from the inside, not from the volume, right? So we know that the minimum cost is going to be related to the surface area. So let's build our surface area. We know we have 6 sides to work with because the top is actually going to be material out the top. So the base here, what's the area of the space here? 3x squared. Is there another 3x squared? Yes, above, right? And then the sides, what's the smaller side here, area of the smaller side? X times H. There's 2 of them. And then what's the area of the front side here, vertical side? 3xh, and there's a 1 on the back as well. All right, so there's cost associated with each side. The bottom and the top is going to be most expensive. $10 per square foot. And everywhere else, all the vertical sides are all a little bit cheaper. The material is a little bit cheaper there, so it's only $6. Okay, so once we multiply the cost into the surface area, we're able to create our cost equation. And we're going to ultimately try to find the derivative for this cost equation here. Okay, 60x squared plus 48xh. Any questions there? All right, so we want to find the derivative for cost, but we know there's something that's sticking out that's preventing us from moving forward. We do need some help. We need a secondary equation to help us get rid of that variable. So that's going to come from the volume. Okay, so volume is 50 cubic feet. But we can also build the volume formula. Looking at our diagram here, length times width times height, that's our volume, so 3x squared h. Solve for h. Okay, yeah, I can't really reduce that, so take that h value and insert it into the h of my cost equation, right? Because I'm trying to, I know my cost equation is going to be what I'm trying to clean up, trying to eventually find the derivative for. Okay, 48 times 50 divided by 3. Now, if this ends up being a fraction, then you can just pull that fraction out and pull the x up to the top, right? So if it's a fraction, just treat it like a number still in front of the variable and get it ready for Powerball. D prime. Once we have our cost equation reduced down to one variable, cleaned up, we can go through our derivative. And from here, it should just feel like something that you're very familiar with, right? You're just find the critical point, right? Once you find the critical point, you're done with the calculus and you're just trying to figure out, okay, what's the problem asking for me to find? Cross multiply here. $800 over 120. Reduce to be 20 over 3. I take the cube root, get a decimal value. Okay, I have my x. I have one side, I have the short side of my dimension, right? So now I need to find the dimensions. So I have 1.882. I'll insert into the multiply the 1.882 by 3 to get the longer base length. And then I also can find the height by inserting 1.883 into the 50 over 3x squared. And then finally, I can find the cost. And we have a bunch of cost equations, right? You can use any of these. They're all gonna give you the same result, but I would just pick the one that I feel is the easiest to plug in.
Question specifically mentioned that we need the supply cost? I don't think so. Just determine the dimension.
Oh, yeah, you're right. Yeah, determine dimensions that will minimize the cost. But on the test, I will say find the cost. Yeah. Thanks. Okay, I'll come around, see if you guys have any individual questions for me. But I think that
So sorry.
Yes, that's the thing. Oh, okay. This is.
Oh.
Yeah.
1.8 into this. Yeah, I literally am like taking that in calculation.
Oh, for the first year, you're gonna see it, it's gonna see more, you're gonna have a line of station. I'll make it very simple. Yeah. The first one is one of their, it's such a graphic way.
There's no absolute background. It alternates anyone.
But then the max, yes, the maximum.
Thank you.
Second derivative test, I will have, I'll say, find the relative maximum using the second.
Okay.
In the EBT, it'll be finding out the max.
Or you just, it's so, okay, and you would just do like.
Mr. Jones, like, you know. Yeah, it's like, you know, something like, say comparison covered, like, what's the, just on that, in 9 days. Because I know that we're gonna, I told her I was gonna go to the lunch, so all the, you just gotta make those in the house. Back to my, it's that, my favorite. I find out it's not really fun for us.
So, wait, oh, okay, that makes a lot more sense. Yeah.
That's number one swimming.
It's not just like this.
Yeah, but this, you gotta do both sides. That's both sides.
My bad. If you didn't do that first, isn't it?
And on the test. And I don't think the stone's even much. It's just the nice my head was covered.
Yeah.
You're like, no, I'm like, I think you're mature.
To that, but yeah.
Yeah, I was gonna send me home. I just took off the like, nail it, okay, good. That's my hair. Then it's like.
Yeah. Yeah. Yeah.
Bye. So, yeah. It's open. So let's say you give here, you would go down to F prime. From F prime, you're going to find your purple.
Okay.
Because these are the candidates, right? The candidates are relevant. But from here, you're not gonna do a timeline. You're gonna stop here, you're gonna just pause. I'm gonna use this as my candidate, but I'm gonna have to do it a different way.
Okay.
So now you're gonna make it on the second spot. So now you're gonna plug the first one into the secondary. And then if you plug in, you can look at that number. If this number is less than 0, it's if I plug in, if I get a positive number, I mean, it's gonna give up, which is that at this point. But then if I want to have full order pairs, I gotta select this back into the different function. Get the, I don't want to call this, I can't say any comma 32. That 32 is.
Yeah. Okay. And then, they can ask for where. Okay. Yeah,
Yes, that's like you can repeat. You take it to F prime, you're gonna set it at y 0, solve for x. And then by f of y, you're gonna plug these values into the f of y. And then the number that you see is gonna tell you whether the graph is probably. Negative. And next time, I think it's increase. I think if I plug. It's like this. Thank you. What's fucking 32? We'll try to do if I get a positive. At 32. Yes. What started here, here. That is to help you so that you don't lose track of it. Look at those fractions. Plus 6. Now this reduces. This doesn't reduce. And then anything that is reduced. Guys, I need all your book bags in the front.